Okay, I'm going to look at two different examples based on what we saw yesterday. The first example, I'm going to look at the equation y prime equals cosine 2t times sine of 2t plus t. And the first thing to notice here is that there's a y prime by itself, and y does not appear anywhere else. And notice that on the right-hand side, it's only a function of t. So this implies that y is a function of t. On the left-hand side, I only have y, or the derivative of y with respect to t. And on the right-hand side, I've got a function of t and t alone. And this means I can take advantage of the fundamental theorem of calculus. Now I'm going to take an integral, and I got to be a little bit careful here. Now there's two different kinds of integrals from remember Calc 2. One is something that looks like this, and the other, it looks the same except that there are bounds on the integral. And it's vital that we recognize that this is just notation for the antiderivative, and this is the definite integral. So this is area under the curve, and this just means I'm going to find a function whose derivative is f prime. And which one I use depends on the particular situation. But also I want to be careful and note that if I look at this integral now is a function of time. This s isn't a real thing, right? This just means if I have some function f, let's go from t, I look from some domain from a to t, what I'm doing is I'm trying to find the area or the signed area under that thing, and as I change t, that area is going to change. So this is now a function of t. So let's go back and take another look at our differential equation. So what did I say? I said y prime is cosine of 2t times sine of 2t plus t. I have just a y prime by itself on the right, and a function that only involves time on the right. Sorry, on the left it's y prime. So that means it's a function of t. But notice, if I replace the t with an s, it's not a big deal. I'm just changing that. And the way I wrote it originally on the left, it's dy dt. But if I take a derivative with respect to s over here, it's going to be dy ds. So I want to make one change to this. So this was the example we looked at before. And the change is, if I take my dE, suppose I know that when t equals 0, the height of the function is 3. So that means that when t is 0, I know my function goes through that point, but I don't know what's happening anywhere else. And so because I know that one extra piece of information, that's going to make my solution to this unique, and I'm going to use a definite integral. Okay, I don't have to do it this way, but I want to follow what happens in your book. So the situation now is y prime equals cosine 2t times sine of 2t plus t, and when t equals 0, I know that y equals 3. So we're going to refer to this as the initial condition, or I'll abbreviate it as IC. So now, when I look at my differential equation, I want to take an integral, but I need to be careful here, because if I take an integral with respect to t, that t is going to go away. So let me rewrite this. Instead of t, let's say it's s. And now this is dy ds. If I do that, I can now take an integral with respect to s, and because I know that I'm going to start at t equals 0, I'm going to take a definite integral, and I'm going to go to some unknown time t. This is now a function of time, and the right-hand side is now a function of time. Okay. And the thing to note here is that for this, I can use the fundamental theorem of calculus, which says that the integral of the derivative is just the original function, but because it's a definite integral, I'm going to go from 0 to t. Okay. So now, looking back at my original function here, the left-hand side looks like y of t minus y of 0, and I know I'm going to plug in 3 in here later. The right-hand side, this should be a 2s, is the integral of cosine 2s times sine of 2s plus s. And I'm going to break this up into two pieces so that I can deal with each piece separately. So the integral of the cosine sine plus the integral of s ds, and both of those are from 0 to t. So now this becomes y of t minus 3. And I'm going to look at this integral of cosine 2s times sine of 2s ds. Integral of s ds, that's a little more straightforward than the first one, so I'm just going to go ahead and do that. That's 1/2 squared, 1/2 s squared from 0 to t. This is not trivial, but notice the derivative of sine of 2s is kind of like cosine of 2s, but I'm off by a factor of 2. So that means I can use u substitution to handle that. So what does that give us? That means now that our differential equation has been reduced to this integral, I had 1/2 s squared from 0 to t. Here I'm going to do a u substitution. I'm going to let u equal sine of 2s, and the derivative of sine of 2s is going to be 2 times cosine of 2s. And this is what I have here. So I have, since 2 is a constant, I can pull this over. And my cosine 2s ds is what I have in my original right there. Okay. So my bounds are s goes from 0 to t. Cosine ds is my du. Sine of 2s, oops, I gotta be careful. Cosine 2s ds is 1/2 du. And sine of 2s is my u. And then the 1/2 s squared, I'm going to plug in my bounds to get 1/2 t squared minus 0. And now the integral of 1/2 u du is going to be the 1/2 times 1/2 u squared. S goes from 0 to t. And the 1/2 t squared gets carried from above. Now this is in terms of s, so I'm going to bring back what my value for u is. So this becomes sine of 2s squared, where s goes from 0 to t. 1/2 t squared just follows. Now plugging in my bounds, this is sine of 2t squared minus 1/4 sine of 0 times 2 squared plus 1/2 t squared. Oops, maybe more careful, 1/2 t squared. Sine of 0 is 0. So I get that y of t minus 3 is 1/4 times sine of 2t squared plus 1/2 t squared. And now I can add 3 to both sides. that is the solution. That's a unique solution. There's no ambiguity. All right. Let's look at another example. And in this example, it's not going to have an initial condition. Let's look at this example now. Y prime is t e to the t plus 3. Notice there's no initial conditions. And because of that, I don't have to worry about whether I'm going to use a definite or indefinite integral. Basically, and I don't know what's going to be given to me later. So I'm going to use an indefinite integral in this case. But having said that, I only have y prime on the left, and I only have t on the right. So again, this is saying my function is a function of t, and then when I say y prime, I've got dy dt. So what is my differential equation? My differential equation looks like that. I don't have an initial condition, so in this particular case, I'm not going to use a definite integral, and I don't have to worry about playing games with my independent variable. So I'm going to take an indefinite integral with respect to t. In doing so, I just need to find an antiderivative of y prime, and that's just going to be y of t. And the right-hand side goes for right. Now, I got to be a little bit careful, though. Whenever I take an antiderivative, I'm going to be off by some constant, c1. Now, I'm going to have an antiderivative on the right-hand side, so that's going to give me a constant. Later on, I'm just going to combine those things together and just say I have a single constant. But I'm going to be a little pedantic here to make sure we can see why that's the case. So I'm going to call this constant c1, but note I'm going to get a c2 on the right-hand side eventually when I do that antiderivative. And when I subtract it from both sides, I'm just going to combine it together. All right. So now I'm going to focus on the right-hand side. I've got two different integrals, just like before. So I can break it up into two pieces. One piece is more straightforward, so let me just do that. So that's just going to be 3t, and again, I'm going to have some constant of integration. I'm going to get a constant of integration from there, but I'm just going to let that slide and refer to it as just this one because it's coming from this one integral. Oh, now I got to deal with this, and all that stuff you did in Calc 2 still matters. Notice I've got t times something, and I can deal with that antiderivative of the something. So what I'm going to use here is integration by parts. So I want to take the derivative of that, which means my du equals, my u equals t. Once I make that decision, everything else is fixed for me, because that means my dv is going to be whatever's left. And that implies that v is the antiderivative of that, which is e to the t, and my du is going to be the derivative of that, which is going to be 1 dt. Okay, so I'm going to get that the integral of t e to the t dt is u times v minus the integral of v du, but then the antiderivative of e to the t is just e to the t, and I'm going to have to add a constant there. So what do I have? Plugging back into here, I now have that y of t plus c1 is t e to the t minus e to the t plus 3t plus some constant. And what my goal is to find this y of t, so I can subtract that from both sides. But notice c2 minus c1, if they're both constants, that's just another constant. I'm just going to call that c. So I'm going to have y of t is t e to the t minus e to the t plus 3t plus some constant. And notice here is I don't know the value of this constant. So I've got infinite solutions. All right, and that's going to be really important later. We need to be very careful. If I were to tell you later on that, say, y of 0 is 5, I can now figure out what that constant is. Because when I plug in t equals 0, I know that y of 0 is 5, so this is going to be 0 minus 1 plus 0 plus c. Add 1 to both sides, and that's going to give me my value of the constant. Okay, last thing. We're going to be working with differential equations, and oftentimes it's going to be in this form. Sometimes it's not. But if it's in this form, we can make decisions about the solution itself. And we're going to refer to this as the qualitative behavior. So we can ask, does it grow? Does it decay? Does it level out? Right? We can ask, is it stable? This is basically whether or not it goes out of control. And we can do that by just looking at that thing without solving it. And that's a very powerful idea, because if we have a physical system and we decide this is our model, before we go to the trouble of solving it, we can ask whether or not it gives us intuitive results. And if it doesn't, that means there's an issue somewhere. It could be in our model, could be in our solution technique, but we can avoid a lot of problems. And so that's going to be the subject of the next day's lectures. But before we do this, I want to just give a preview and talk a little bit about the derivative. And this is going to be a bit of a refresher. So what is the derivative? So if I've got some function y of t, and I'm interested in what happens at some point a, the derivative is going to be the slope of the tangent line. Okay. So why is that important? It's going to tell us whether or not our function is increasing or decreasing, and by how much. So suppose I have this is my function, and I'm looking at two different points. So at A, if I have this, my function is increasing, which means that my derivative is positive. So if the derivative is positive, my function is increasing. And if I look over here, in this case, it's decreasing, so the derivative is negative. So this means my function is decreasing. Now we've got to be a little bit careful here. Suppose I tell you that y prime of some function at d is 0. By itself, that tells us nothing, right? Because we could have a situation where it's a max or a min, but we could also have a situation where it just levels out and then is still increasing, but the derivative is 0. And likewise, I can have a situation like that where the derivative is 0, but it's a decreasing function. So the y prime equals 0 case is something we have to be a little bit careful about. But having said that, oftentimes we're going to see functions that do something like this and basically level out. And notice in this case, y prime gets close to 0 for all t greater than or equal to some number that we don't necessarily know yet. Okay, but once I get past this point, the derivative is close to 0. So to cap off, what do we know? We know that if y prime is greater than 0 at t equals a, y is increasing. If if y prime is less than 0 at t equals b, y is decreasing. I can be careful. This is at t equals a and this is at t equals b. And if y prime equals 0 at some t equals d, we don't know. Okay? And what we're going to see next time is we can play a game, is we can say, suppose we know we have some function, and suppose we know it goes through that point. If I can calculate its derivative, right, that means I can calculate the tangent line at that point. And if I can calculate the tangent line, I have an idea what the function looks like if I were to just focus in and look real close right there. I can have a good idea of what's happening with that function.